to YouTube as well. So I'm gonna see my stream in about 10 seconds, on my browser. I just need to confirm that before I move on. All right, so the YouTube part is working, and I haven't checked the volume yet. Let me check that too. Yep. Okay, so the YouTube stream is definitely getting the audio too. So I can basically not pay attention to that window anymore. And now I'm going back to Discord, and everybody seems to be doing okay now in terms of being able to hear the voice. All right. So we got 1 minute and 15 seconds or so. So I always start on time, at exactly 7 p.m. If you guys have any questions, before we get the class started, you can always, ask those questions either by direct messaging me on Discord or using the channel, the text channel of the day. So it all depends on whether you want other students to be able to see what you're asking. So this is why I really like this course. It's really easy for me to manage real-time communication during a synchronous lecture, and I personally prefer a synchronous lecture as opposed to asynchronous. But since everything is recorded, so if you cannot make it to the synchronous lecture, you can always just watch it asynchronously. But I do recommend that you watch it as soon as possible, so this way we don't have a whole lot of material kind of built up. And catching up can be difficult in this class, especially when we get to more advanced topics. All right, so we got about 10 seconds, and I'm gonna do one last check on my Discord server to make sure that I am assigning a student role to every person, every member who signed in. And I got one person who has not changed the name to include a last name initial. So Shirsha, S-H-I-R-S-H-A. You might want to add a last name initial. And we also got another one with a name of XCHCX, CHX, sorry. So also make sure that you change your name or nickname to include your last name. So at the end of today's lecture, anyone with a nickname on the server without, following the format is going to be kicked. So I'm just double checking everything here. They all look good. All right, so we are already 1 minute into 7 o'clock. So we'll go ahead and get started. I'm not going to spend a whole lot of time to talk about the syllabus because I already sent you a video talking about it. All right, so Andy, you might want to mute your mic because I can hear myself through your mic. Thank you. So in general, if you guys want to use the voice channel to ask questions, I don't have a problem with that. It's just that, if I can hear myself through your mic, that gets a little bit confusing. So we'll go ahead and make sure that the mics stay quiet unless you have a question to ask through the voice channel. All right, so the syllabus is pretty much done already, except for the part that is specific to this class. So the parts that are specific to this class would be the tentative schedule of topics. And I really need to revise this because I changed the ordering of these topics quite a bit. Even though I end up covering the same topics eventually, the ordering, is not exactly the same as this. So, so don't count on this schedule, for the topics. On the other hand, you can go to Canvas, and the ordering of what appear as a chain, basically these are all links to external material. These are all correct. Okay, so we are basically going to talk about physical states, numbers and computers, and then the next thing we'll talk about would be values, numbers, and bases. Basically, it talks about base conversion, and then we will talk about adding numbers in base 2. And then we will talk about Okay, I forgot to hide this one. I'm gonna have to hide it first. Then we'll talk about subtraction of numbers in base 2, signed value representation, and so on. So I'm gonna hide some items here because they are not things that you can do at this point. So I will unhide items as we go to those particular labs. So basically what you need to do is to read the modules in the sequence that they appear in Canvas. Okay, so that's essentially how you can prepare for classes. Okay, it's good to be able to read a little bit before the class. I know I didn't give you guys any reading assignment before today because today is quote-unquote the first day of class of this section. The other thing is because I do the lectures in a synchronous mode, and I'm glad that most of you can make it to the synchronous session. I think that's great. But this also means that we're going to follow the final exam schedule. Basically, we'll use the schedule of classes where the start time is 7 p.m. on Tuesdays and Thursdays. So I will go ahead and look it up and put the actual final exam time into Canvas. So that would be our actual final exam time, and you probably want to plan ahead of time and make sure that that time slot is available at the end of the semester. All right, so I will get to this row-taking activity in just a little bit. But before we do that, we are going to get started with physical states, truth, numbers, and computers. So I'm going to open the new tab. The HTML link is the one that will stay updated. The PDF one, unfortunately, is not going to stay updated for much longer. The reason has to do with the tool that I use to generate the PDF version is not accessible anymore. So it is not accessible to people who use special software to look at the organization of the document. On the other hand, the HTML document can be used to regenerate the PDF if you want to. So we're going to rely on the HTML version of the document. All right, so I'm just checking, making sure that we do not have any questions. There we go. All right, so let's go ahead and start with physical states. Okay, I know there are a lot of words. I'm not expecting you to read it right now, okay, but I do want you guys to read all the modules eventually. Okay, so after class, sometime before Thursday, I really want you guys to read the entire module. So when I talk about physical state, okay, the best thing you can do is to kind of imagine in your head that you have a voltmeter. Okay, so even if you have not taken any electronics classes, most people kind of know what a voltmeter is. It has two probes and it measures voltage, okay, or electrical potential between 2 points. Okay, and electrical potential is a physical quantity. It can be measured using an apparatus like a voltmeter or a multimeter. Other physical states include the flow of water, okay, which you can actually see, when water is flowing. The flow of air, okay, so pneumatic devices, rely on the flow of air. So that's kind of what we are talking about when I talk about physical states, okay? Air pressure, airflow, electrical potential, electrical current, and so on. Those are all physical states. So what is cool about physical states is that they're real, okay? If I give you a battery, okay, and I said, let's make sure that this battery is still good, okay? Most alkaline batteries should measure, when they are full, they should measure 1.5 volts across the terminals. So you can get me a voltmeter or a battery tester. You can put the battery into the tester, and there's usually it's either a number, a dial, or a needle that will indicate, yep, this battery is still good, okay? So we can check physical states because they are, guess what, physical, okay? So we'll start with that before we move on to other stuff that is a little bit more abstract. These sections talk about different types of technology that people have used in the past to implement computers. We start with electromechanical devices. So electromechanical devices are still used today, even though they are being used less and less, these days. But if you look at most cars under the hood, they still contain relays, okay? And relays are electromechanical devices because there's the electro part, which is basically the magnetic coil that gets energized when current passes through it, and it creates a magnetic field. And then the mechanical part has to do with a lever that is usually, at least a part of it, is made out of ferrous material. So it does get attracted by magnetic field. So when the magnet is actuated or energized, then there's a little lever that actually physically moves to close a contact or to open a contact, depending on whether the relay is a normally open or normally closed kind of relay. So electromechanical devices are still being used, but they are being used less and less often because they are actually more expensive to make compared to what we call solid-state devices. But in the context of this particular module, we are talking about what components do people use to make computers. And at one point in time, people do use electromechanical devices to make computers. So I'm going to open a new tab here to show you what I mean by that. If you want to kind of visualize, okay, the best way to do it is to watch the movie An Imitation Game, because in that particular movie, Alan Turing, okay, which is a historical figure, okay, and he's also in that movie. So the computer that he made in that movie was a computer that uses electromechanical devices. So if you look up an imitation game, oh no, just imitation game, imitation game movie, and we want to look up the computer specifically. So there we go. So this particular clip here, has a good view of what the mechanical device look like. So if you click on it, and I'm gonna have to turn off the volume. So you can see how big this thing is, but it doesn't use relays. It uses what we call rotors that rotates. So as the rotor rotates, it will connect different points on the dial, to another point. And that's how it changes, quote unquote, its configuration. And that's basically how a electromechanical computer works. And as you can probably imagine, it cannot be very fast, right? Because electromechanical devices rely on, I'm going back to my notes here. Oh, there we go. This is the correct one. So electromechanical devices are slow because they rely on either rotation or a lever, responding to a magnetic field to close or open the contact. So they're pretty slow by comparison to non-electromechanical devices. But back then, in the late 1940s, that's pretty much the only technology available to Alan Turing and his team. So that's why they made computers using electromechanical devices. The other thing that's kind of unique about electromechanical devices is they are actually noisy. Okay, they actually make audible noises that you can hear, like lots and lots and lots of clicking noises. Okay, so from electromechanical devices, we moved on to vacuum tubes. This is an actual link to Wikipedia, and you can look it up in Wikipedia to find out how vacuum tubes work. So vacuum tubes are slightly better compared to electromechanical devices like relays because there's no moving parts, okay? Well, I shouldn't say no moving parts. I should say, no mechanical moving parts, because guess what? Electrons are still moving in vacuum tubes, okay? But they are not, quote unquote, mechanical devices. And in the discussion of vacuum tubes, one particular type that is really kind of important in our discussion is called a triode. A triode is a switch. Okay, so just kind of imagine the wall switch for turning on and off lights and whatnot. Okay, it's kind of like a switch like that, with only one exception. Okay, so instead of using a mechanical energy or using a mechanical lever to flip a switch on and flip the switch off, it relies on electricity also to turn on and turn off, the switch. So this is the key to, what devices can be used to make computers, okay? It has to be made out of switches, and what is special about these switches is the quantity that it is switching, which can be the flow of electrons or the flow of air or the flow of fluid, is controlled by the same kind of quantity. So we are using an electrical potential to control the flow of electrical potential. We're using air pressure to control the flow of air. We're using the fluid pressure. This is hydraulic. So we're using hydraulic pressure to control hydraulic action. So that is the key of what kind of devices we can use to make computers, okay? So looks like we're still good here. All right, so getting on to vacuum tubes. So vacuum tubes are not mechanical, which means they may not be as power hungry because it takes quite a bit of current to actuate a coil, electromechanical coil. But vacuum tubes are not really that energy efficient either, because in order for vacuum tubes to work, there has to be a heating element at the center of a vacuum tube. So vacuum tubes from the outside, they look like light bulbs, except they're not really bright, okay? They are just kind of dim, but they are lit, okay? And that's because, there has to be a heating coil, that has to be, at least appears to be glowing from our perspective, in order for electrons to be freed from on the surface of a conductor. And as a result, if you have a whole bunch of vacuum tubes, just heating up the vacuum tubes is going to take quite a bit of energy. But vacuum tubes are fast because they are not mechanical, so we can now have computers that are quite a bit faster compared to other computers. And there are computers making use of vacuum tubes, and this section, these paragraphs will get to those particular computers. So there's the Lorenz cipher, which is a more sophisticated decipher or decryption machine compared to the bomb. The bomb was the one that Alan Turing was inventing. This is another one, but this one uses vacuum tubes. So eventually we moved on to transistors. So transistors is very interesting because the name transistor comes from resistor, but it is called a transistor because the amount of resistance is variable. It can change, okay? So what is even more interesting about transistor is the material that we use to make transistors, which is mostly silicon, by itself is an insulator. It does not conduct electricity. So the reason why transistors actually conduct electricity has to do with what we call quote-unquote impurities. So impurity elements introduced into silicon, the process is called doping. Okay, so doped silicon becomes conductors. Okay, but that's also not what we want, because we don't want transistors to be conducting all the time, because remember we want switches. We want them to conduct sometimes and other times not to conduct. So okay, I got a question, so let me go take a look here. Okay, so I got one of the students who did not sign up on Discord early enough. Okay. So anyone who's signing up after the class starts obviously will not be able to get into the class without me distracting the entire class to go there to let that person in. All right. So let me respond to that person and say that he or she can now get in. Okay. All right, so now getting back to the class. All right, so getting back to the class, transistors, very, very interesting devices. I'm not going to talk about the PN junction and how there are two main types of transistors. We got BJTs, which stand for bipolar junction transistors, and we also have FET or FET transistors, which stands for field effect transistors. So I'm not going to talk about the actual physics of transistors, because I'm, guess what, not a electrical engineer. I am a computer scientist. But what is interesting about transistors is they are also like the other two types of devices. They are switches. Okay, in this case, with a FET or field effect transistor, we use electrical potential, or otherwise known as voltage, to control a transistor to let it either conduct electricity or stop the flow of electricity. Okay, so for the most part, we are going to focus on transistors in this class. Well, at least for the first or two lectures, and then after that, we're going to step away from the discussion of transistors. Instead, we'll be talking about gates, which basically are Boolean operators, but implemented as real physical devices. Okay, all right. So, do we have any questions up to this point? Basically, it's just a quick history of what devices we use in computers, going from electromechanical devices to transistors. So I'm keeping an eye on the text channel and see if there are any questions. And I'm not seeing any. Oh, okay, we got Tom typing. No, this stuff is kind of hard to be quizzed. All right. Anything else? We got a few other questions. Okay. It's interesting. Yep, it is interesting. Computers are interesting in many, many ways. So, since people are talking about interesting, I'll tell you something that is really interesting. Transistors, okay, people started to use transistors to implement computers as early as the 1960s, okay? So it took maybe around 20-ish years, okay, to evolve from electromechanical devices through vacuum tubes, and then we got to transistors. So we started using transistors in large mainframe computers in the 1960s. So now we are in the 2020, right? This year is the 2020. So we are talking about 60 years, okay? COBOL as a programming language is 60 years old. I'm just trying to remember, is it 60 or 50? I believe it is 60 years old, okay? COBOL as a programming language is 60 years old. And COBOL only ran on computers that were that used transistors as components. Okay, so that's why we know we have been using transistor for 60 years. So here's the question: how come we are not inventing yet another type of switch to be used in computers? Okay, we didn't stay with mechanical devices, electromechanical devices for too long. We did not even stay with vacuum tubes for too long, at least not in the United States. Okay, but we stayed with transistors for a long time. So were there any changes since the 1960s? What do you guys think? What changed in 60 years? What is the most significant change in these 60 years? Exactly. Okay, I have Elijah also typing. Yep. Okay, so they're both correct. Okay, so Aiden and Elijah are both correct because the size of each transistor affects how many transistors we can fit into a small surface or space. Okay, so we are talking about, let's check it out. Okay, let's check out size of transistor in 1960. Okay, and Google says, no, it doesn't say the size of a transistor back then. Yeah, it has a little bit to do with that, Tom. So if you look at transistor count, it'll probably, oh, there we go. This is a nice graph, by the way. So if you magnify the graph, you can see in 1970, not quite 1960s, and I'm just trying to see, they tell you what the processor is. It's the Intel 4001, so we can look that up. So Intel 4004, okay, I misspoke. It's 4004 transistor size. Okay. So this is 1971, which is 10 years after the mainframe computers started using transistors. It is a 32 nanometer process die and second generation high-K metal gate silicon technology. 32 nanometer. That doesn't sound right to me. Okay. Okay, that's more like it. 10 microns. Okay. All right. So let's think about this just a little bit. Okay, this is really interesting because most people, would think, oh, we are now down to 7 nanometers, and this one is 10 micrometer. So it's not really that much bigger than what we have now. Is that right? Well, micro and nano are quite different, aren't they? Okay. 1 micro is 10 to the power of -6, and 1 nano is 10 to the power of -9. In other words, the transistor inside the processor in 1971 is, let's see, 10. It's basically 1,000 divided by 7. Let's see, am I right? No, it's 10,000 divided by 7. Okay, that's the ratio of the change of size of transistors from 1971 to today. Okay, no other technology has seen changes like this because if you look at a car, okay, if you look at an automobile, back in 1971, and you compare the engine design to an engine of a car today, obviously you will see a lot of changes, right? Fuel efficiency is much better, blah 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 blah, and so on. But you're not looking at the same kind of order of magnitude. Okay, a car today is not 1,000 times better than a car from the 70s. Okay, it's not. Okay, you might be looking at twice as good, maybe pushing 3 times at the most. Okay, but not 1,000. Okay, but in computer technology, the size has shrunk so much, in basically a really short amount of time. All right, cool. And this slide here, it talks about Moore's law. For those who are interested, you can look a little bit more into Moore's law. Moore's law basically says, we can double the density of transistors in a processor every 18 months. Okay, so every 1.5 years, we can double. And that's really kind of something, because when you look at this graph here, you can kind of see that when you kind of more or less connect the dots using a straight line, that line is pretty linear. Okay, but the scale, the y scale, is not linear. The y scale is actually exponential. So that means the number of transistors we can fit into a processor, or the transistor count inside the processor, actually has been growing exponentially, and it's still growing. May not be exponential as before anymore, but if you just look at the count here, we went from somewhere like maybe 2,000 to 50. Let's see, 50 billion. Okay, so we went from about 2,000 to 50 billion in just less than in about 50 years of time. And you might think, but 50 years is a long time. Tech, you're an old man. Well, that may be the case, okay, when you look at the lifetime of a person. But there's no technology that has seen this type of change in just half a century. So we are looking at, if you project into the future, okay, because that concerns you, okay, you guys are young and you have a lot of years to come. So if you project this into the future, the changes are only going to occur faster and faster. which is great from one perspective, but it can also be stressful in another perspective. But we'll kind of talk about that stuff, in a different setting. Okay, so continuing on with transistors. And by the way, the word transistor is the word that you need to use for row-taking activity today. Okay, just transistor. Let me make sure that you know what I'm talking about. And I'm just getting to a text terminal so I can type it. Okay. Oh, there we go. And this is CISP310. I'm just making a text file. So the word transistor, singular, is what you need in order to quote-unquote take row today. And the activity is already up on Canvas. So when we take a break between the lecture and the lab, that's when is a good time. That's a good time to go and just kind of type the answer in and be done with it. All right. Oh, I'm going back to Tom's point. Okay, so Tom's point of AMD is now going to 7 nanometers. Okay, and they're basically that's in production. That's as small as it goes when it comes to making transistors smaller. There's only one answer on the quiz for row, yes, and it is transistor. So if you type transistor in that quiz and just press the enter key, I think you should get full score for that. And then Aiden has... Oh, I did? Darn. Okay. All right. Well, I guess that's a freebie today, right? As long as you get points for that quiz, it's good. So if it doesn't give you points, then I'm gonna have to give you a different quiz. Does it give you points? Yep. Okay. Well, that counts. All right. Cool. Okay. My mistake. I forgot to change the type of question instead of using a... Yeah. Exactly, Daniel. Okay. Cool. All right. So what we'll do now is to focus on transistors. Okay. And we want to make devices out of transistors now, okay? So here we have, oh, okay, so section 3 is a really short one that talks about quote-unquote truth, okay? So truth and true and false are basically just two values. So now the question is, well, when we look at a transistor and, in a circuit, we can measure voltages, right? We can also measure current, but most of the time we want to measure voltage. So we can measure voltage. It's either this is 0 volt, and this one is old what we call TTL transistors have 5 volt as the quote-unquote it's the voltage of 1 basically. So we have 0 volt, we have 5 volts, and transistors that we use today are low voltage transistors. So a 1 may be 0.7 volts. For those of you who mod your processor, who push your processor to extremes, you probably know what kind of voltage we are talking about, but it's lower, okay? But nonetheless, it is really a difference between 0 volt and some volt that we say, okay, anything beyond this threshold we count as quote-unquote true. So 0 volt counts as false, and then when it gets beyond a certain threshold, maybe 0.7 volts, maybe 0.9 volts, I don't know for sure now. But if it goes beyond a certain threshold, it is counted as a 1 or a true. So now we are... All right, well, it is recorded. I'm responding to a question. So it is recorded, and so you can go back and watch it. All right, and that board is actually on the screen right now too. All right, I'm gonna give people a freebie this time. Okay, it is transistor. So next time, let's try not to get distracted. All right. And you don't really need to know it either because I made a mistake in the quiz. What am I going to do? Anyway, so the concept of 0 or 1 or true and false, those are abstract concepts, right? But mapping those concepts to physical quantities is really easy because it's just a matter of interpretation, okay? You look at a voltmeter, if the voltage is below 0.05 volts or something like that, you just say, yeah, I'm going to count it as a false or a 0. And if the voltage is 0.7 volts or more, then you interpret the voltage and say, I'm going to count it as true or 1. So it really is just an interpretation of a physical quantity that we assign quote-unquote meanings or semantic to the physical quantity. Okay, so now we move on to section 3.1. This is where things start to get a little bit thicker, and things may appear in the exams at this point. Okay, so we have two different types of transistors. We have an N transistor that looks like this, and then we have a P transistor that looks like this. Now you can say, that's pretty clear what the difference is. One has a little arrow pointing up, and the other one has an arrow that is pointing down. But remember, we can always flip the orientation of something in a circuit diagram. So that arrow by itself is not how you differentiate an N transistor from a P transistor. Does somebody want to make an observation and tell me what is the actual difference between an N transistor versus a P transistor? Even if we can mirror flip the image and do the rotation, in all, in 90 degree, 180, and also 270 degrees. What is the differentiation? The circle. Very good. Okay. So when you look at this circle here, it is only present in a P transistor, but it is absent in an N transistor. That is how we can tell the difference between a P and an N transistor. Okay. So this is also a good time to show you the tool that we'll be using for this class. Okay, it is called Logisim. The instruction to download Logisim is in the notes already, so try not to do that at this point. Okay, so what I'm gonna do, okay, let me show you the screen here. All right. So the way we use Logisim is it is a Java program. It's already compiled, even though the source code does distribute with the compiled bytecode, but it is already compiled. So you say Java on the command line, or if you prefer, I think you can double click on the jar file in Windows and start running it. But eventually you want to learn how to run programs on the command line, because there are only certain things you can do on the command line that you cannot do it in a GUI mode. So eventually you have to learn how to do this in whatever operating system you're using. If you use Windows, there's a way to do it in Windows. If you use Mac OS X, there's a way to do it in Mac OS X. I use Linux, and this is how I do it in Linux. Okay, so you have to learn how to use a CLI or a command line interface in the operating system that you are using. All right, so java-jar, and then we have to specify the path to that jar file. And so in my case, okay, it is tilde/documents/CISP310, and the file name is logisim310.jar. Do not search online and download Logisim from online resources unless it is coming from my shared drive. Okay, the reason is I made some changes from the quote-unquote stock Logisim, so this one is not exactly the same as the other one. For certain type of things that we do in this class, it doesn't really make any difference. For many other things, it does. So you need to go through the lab today, which I'll open at the end of today's lecture, in order to get to this file. Okay, so right now what you want to do, I hope you guys are taking notes on the side. So you might want to take some notes on the side right now if you have not been taking notes. So I'm opening up my own OBS. So if you look at OBS, you will see a timestamp at the bottom here. So you might want to record what time it is right now. It is 7:37-ish, because you might need to come back to this segment of the video to remember how to launch Logisim. And I think we got a question on Discord. Let me go take a look. Okay, Andy is asking, is there a good resource of learning how to use command line in Windows? I'll give you an answer that you may not like. I give a lot of answers where people may not like. It is called Googling. Yes, Aiden got it. So you can look into Windows CLI tutorial or something like that. Yeah, in 15 minutes from Princeton University, no less. So we're not going to do anything super duper intensive with command line interface. For the most part, we just want to be able to specify a file path in the CLI and to be able to change directory. Okay, so in DOS or in Windows, they use slash differently. Okay, so when I use a forward slash, you have to use a backward slash, and you have to know where you put your files. Okay, so that's basically the main differences between the different operating systems. In Mac OS X, it's really close or pretty much the same as Linux. So basically the format of the commands that I use in Linux, can be used exactly the same way in Mac OS X. In Windows, you just have to kind of change the slash from a forward slash to a backward slash. Yep. So so there are many ways to look into and learn how to use simple CLI commands, command line interface. All right, you're welcome, Andy. All right, so getting back to our stuff here and getting back to the command line that I was typing. So what this is doing is I'm telling Java, which is already installed on this computer. So you might want to check this first. Okay, so the first thing you need to do is to type Java, and then I think it is version. Okay, so Java-version. If you do this on the command line interface, regardless of your operating system, it will tell you whether you have Java already installed, and if so, it will tell you which version it is. Logisim is not very specific. It's not very picky about which version of Java is needed. So anything that is at least 1.8 point something is going to be enough. Okay. Some particular programs are much more specific and they need the latest and greatest version of Java. Logisim doesn't really care. Okay. So if you have version 8 or later of Java, you are fine. Okay. So that's the first thing you do. And then the second thing you do is to type the command that I was typing earlier. So -jar is telling Java, which is a virtual machine, that we are providing an archive. So the word jar, J-A-R, does not mean an actual jar. Okay, it is an abbreviation of Java archive. So it's like a zip file. It is a zip file of multiple files, but in those multiple files are the bytecode files, and basically we are telling Java and say, hey, there's a whole bunch of files in the file that I'm going to give you. So from these files, you need to go search and look for specific things to start the program to run. Okay, that's what -jar is saying. So in Linux and also in Mac OS X, the tilde sign is what we call the home directory. So I don't have to type in the full path of home. And then we go to documents. So if in Windows, obviously, you probably have a slightly different path of where you'd like to put things. So you need to change this part accordingly. And then in documents, I have a special folder for everything related to CISP310. And Logisim, .jar, Logisim310.jar is the one that is located in this particular subfolder. So your path in Windows is going to look different, okay? Because the way you specify where you can find a particular file that you have saved is different, but the way you use Java -jar is going to be the same. Okay. So I press the Enter key, and Logisim started, and this is Logisim. So when you look at Logisim, okay, it looks like a program that you use for drawing diagrams or stuff like that, and that is actually true, but it can do a little bit more than that too. All right, so what I'm going to do is I'm going to construct a circuit that is actually in the notes. Let me switch back to the browser first, and I'm going to show you which diagram we are talking about. It's going to be the diagram in figure 3. It uses 4 transistors. So let's go ahead and magnify this just a little bit. So this way you can kind of look at it. Now remember, you are participating with your own computer, right? So you don't have to rely on the shared screen to look at a document that you already have access to. Okay, so I encourage all of you to open up the same document on your own browser. So this way I can scroll, I can go to different types of applications, but your browser, your Firefox or Chrome or Edge, okay, can stay at the same place. So you can actually just keep your browser on this diagram so that you can keep focus on this diagram, okay? So, but in my case, I'm going to switch back and forth, okay, between this diagram and Logisim. So I'm going to switch back to Logisim, and I say, okay, we need a whole bunch of stuff here. So most of the stuff I can find under wiring. So when you click on wiring, it opens up, it's like a subfolder thing. So it's a container containing all of these components. So when you look at these components, each one is like a class in C and C++. In other words, if I say I need a transistor, okay, I go click on transistor, I have just selected a class, okay, and without dragging, so I'm not dragging, I'm just clicking here on transistor, and I'm just moving the mouse pointer into the main area. This is how I instantiate an object out of the class. So this is one object, okay? It is a transistor. But remember, we need 4 of these things. Okay, but I'm not going to drag any additional ones because I can change the property of this transistor. So just like an object in object-oriented programming, every single object actually has multiple properties. This is where you can see the properties of a particular item in a circuit, okay? This one is a transistor, okay? Its type is a p-type transistor. It's facing east, okay? So what is facing east is it's basically facing in this orientation, pointing to the right-hand side. And you can change the rotation if you want to. Gate location is top/left, which basically means, if the transistor is facing east, then the gate location is facing north, or facing, is on the top, and the number of data bits is 1. Okay, so we're not going to change anything yet. Okay, the first thing we want to do is to say, I have never used a transistor before. I have no idea what it is, what it does. So where can I find more information about a transistor? I'm going to give you guys 5 seconds to answer that particular question, and Daniel is right on it. No, actually I'm not. I wasn't gonna say Google. I was about to say help. Help. Yeah. Well, I mean, you got close. I mean, pretty sure Google can answer that question too. But help is even better. Okay, so if you go to the help of Logisim and you go to library reference, okay, you see a smaller window opening. And it looks like a browser because it really is a browser. It's a miniature browser. But it organizes material in the same organization. So you go to wiring library and you go to transistor, you click on it, and guess what you get? An explanation of what a transistor is. Okay? So use this feature of Logisim. A lot of documentation is actually built into it already. Okay? So, but I'm not going to just read the documentation of Logisim. That would bore me to death. So I'm not going to do anything that would bore myself to death. So instead, I'm going to explain it using this picture over here. All right, so we're going to magnify a little bit. So the magnification control is at the lower left corner. So you can just change that percentage to make it look a little bit bigger. So this is probably a good size. So this is a transistor. It is a p-type transistor. So what we see here, with this arrow, it indicates flow. Okay. So there are 3 terminals to this type of transistor. So let me just use regular text to describe the 3. One is called the gate, one is called the source, and one is called the drain. Okay. If I were to give you a guess, okay, if you are asked to guess which one is the source and which one is the drain, just from what you see in the picture right now, what would be a logical choice of where the source is and where the drain is? So Tom is, source is the tip. The tip of what? The top tip. No, that's not true. Daniel has got it. Okay, Daniel and Andy both they have both gotten it, because when we look at flow, okay, there's a source and there's a drain. Okay, so those two words is a pair, because source is what is providing something, in this case positive charge, and drain is what is consuming the same kind of quantity. So the source is always what is providing the quantity, so it is where the arrow is coming from, and then the drain is what the flow is going to, so it is always in the direction of the arrow. Exactly, so Tom is correct. What is left is the gate, and since we already labeled two of the pins, the pin on the top is called the gate. So what you can do is to have kind of a mental picture of a gigantic gate. Okay, I don't know how many of you have seen irrigation gates. Okay, those kind of the gates of a dam. Okay, yeah, not the bad word dam, the actual dam that stops water from flowing. Okay, so if you look at the gate, from that perspective, that is what you use to open up so that you can allow flow, or what you can also close it to stop the flow. Okay, so that's basically what a transistor is. Okay, the gate is the control, the source is where stuff is coming from, and then the drain is where stuff is going to. Are we good on these three terms, to label the three terminals of a transistor? I'm just looking at the text channel to make sure that there are no questions. If you don't quite know what to ask, but you think you do have a question, you can just kind of start typing. If I see people starting typing, I will kind of pause and give you guys a little bit of time. Okay, so I got a comment here that I'm tipping, I'm peaking or saturating the mic channel. So I can try to clip it a little bit, or control it a little bit, and looks like, all right, so I can control it in OBS and reduce it just a little bit. Okay, because I got a comment this morning saying that I'm too soft, and so I kind of need to find the sweet spot for that. There we go. So I think we are better at this point. I'm not seeing the meter turning into red, so I will keep an eye on it. Oh, so Duck is asking, can I repeat source and drain? Source is where the stuff is coming from, drain is where the stuff is going, and gate is what is controlling where the stuff can go from source to drain. All right, cool. All right. Okay, Duck is typing some more. Okay, nice. Okay, you're welcome. All right, so if this is a p-type transistor, how do we make, and what does it look like when we have an n-type transistor? So as lazy as I am, I'm not going to go back here to pull another transistor. I will click on an existing transistor, or better yet, I'll select the transistor and all the labels, and then I type Control D on the keyboard. And what that does is Control D stands for duplicate. So now I have an exact copy of whatever I selected earlier, and now we can now go to just the transistor and say, I don't want a p-type transistor anymore. This time I want an n-type transistor. I'm just looking at the clock to look at the time. So we still got about half an hour, so that's good. So now we can change the type. Okay, we can change it from a p-type to an n-type. Wow, that's not really that different, is it? Because if you look at the p-type transistor, which is this one here, and you look at the n-type transistor, the only difference is the bubble is gone. How did I do it again? I went to here and I changed the type. All right. Okay. Cool. So from the questions, I think it's a good idea for you guys to kind of create your own catalog. So when you notice me starting to do something, just kind of jot down the time really quickly, because the time on your screen is about here. And once you note the time and you know when the lecture starts, you can go to that particular segment in YouTube really, really fast. And there are ways you can create your own URL to go to a particular time mark in a YouTube video. So you can basically create your own spreadsheet of, just shortcuts to get to various parts of my lectures. So this will help you when you need to review the material, when you just need to go, I just need to look up how to create blah, blah, blah. So you just look up your own notes and your own indexes, and then you can quickly locate it and go like, okay, I know exactly how to get there. Just click and you're there. All right, we got Mustafa typing, so I'm gonna wait a little bit and see what the question is. And by the way, if you guys think my the image of me, on camera is disturbing and it's not really helping to make the lecture more, I'm just thinking of the term that this district is using. Engaging, that's right. Okay, so the district, okay, the Los Rios district, wants the online classes to be more engaging, and the distance education coordinators basically said, well, if you turn yourself into a person by including an image of you doing stuff, then people would know that there's actually a person behind the screen, and that makes it more personable. That's why you're seeing me, as in the video. But if you think it's too much and you don't want to look at my face, you can probably put a duct tape on your own monitor to block it off, or I can turn it off too. So if enough people are requesting, please do not show your face anymore, I'll turn it off. Not a problem. All right, so Aiden is typing. You don't even need to know the channel, Mustafa, because remember, I sent you guys a lot of announcements. And also, there's also the at the beginning of each day in Discord, there is a pinned message, and that pinned message has a URL to the lecture recording of that particular day. That is how you can quickly locate videos related to this class. Now, if you want to go to YouTube and go to my channel, which is Some Profs, and search for lectures over there, that's fine too. Okay, I'm just trying to give you guys a shortcut so you don't have to do that. Not to kill the face, but kill the person behind the face. Oh, okay. Well, that's kind of interesting. Okay, cool. So now what we do is we are going to construct the circuit. Okay, so I hope you guys are still having your own browser. You're looking at the circuit. So what I'll do is I'm just going to create a circuit over here. So as I create a circuit, I'm going to explain what I'm doing. So this is called power. Okay, this is kind of like the positive end of a battery. Now, when you look at every single component I put into the circuit, not everywhere within that item is quote-unquote connectable. So if you hover your mouse pointer over various parts, there's only certain parts where it will turn into a circle. That is a connection point, okay? Or you can just call it a connector, okay? So with power, there's only one connector because it is just supplying positive voltage. But when you look at a transistor, there are three connectors. There's one connector here, one connector here, and one connector here. So when we need to make a connection, so which is what we are going to do next, we have two p-type transistors on the top. So I'm going to take this one and duplicate it. Okay, so now we have two of the p-type transistors. I'm just looking at the text channel and just kind of chuckle a little bit. There we go. So now we look at these two and go like, that doesn't look like what the circuit displayed. Well, that's because we got rotation, right? So we have to rotate these so that the source is pointing to the north, and then the drain is pointing to the south. And by the way, you guys are looking at the video, with my picture in it, and it looks like I'm looking at you, right? Pretty close, okay? It's pretty close of me looking at you in terms of eye contact, and that's because I have a little device that has a half mirror or what they call a beam splitter. So when I look, so it's kind of transparent, in a way, so I can look through that mirror onto my own screen, but it's also a mirror at the same time, so it reflects my face, which is lit on the side, to a camera that is sitting on the side, okay? So that's why, when I look at the screen, it is almost as if I'm looking at you to maintain eye contact. Yeah, it is pretty cool. It's kind of the same kind of technology that people use in teleprompters, except I reverse it. In a teleprompter, they use a half mirror so that the speaker can look at the audience, and then the half mirror would reflect the actual text for the speech. I'm just reversing it so that I can look at the screen, but the camera can also look at me through the mirror, so that it can do all the recording and streaming onto YouTube and also Discord. So it's a pretty neat trick. It takes me a while to kind of figure out how to get this stuff working, so it's kind of cool. All right, so getting back here, sorry for the distraction. So at this point, I'm not going to label the pins anymore, so the labeling kind of goes away at this point. So what I need to do is to turn it clockwise by 90 degrees. Now, since I have to turn both of them clockwise, I can now select both and then go to facing, which has to do with the rotation of a particular item. So instead of making it face east, I want them to face south. Okay. So now I'm turning both to face south. One is already in the correct orientation. The other one still doesn't look right? It doesn't look like what you see in the other picture. And that's because the gate is on the wrong side. And that part is controlled by gate location. So instead of being on the top or left, in this case, I have to flip it to the right-hand side. So now, they look right, okay? All right. So here's the most important part. Okay, when you look at the completed circuit, there's a wire connecting both of the source pins of both of the p-type transistors to the power. Okay, so this is the important part. If you try to make a wire from not really the terminal part, it's not going to do it. So I'm just trying to. Okay, let me make a really bad diagram here. Okay, so this, you can see how the bright green is extending, because that's basically a 1. But if you connect it to the wrong, quote unquote, if you connect it to the wrong point, it's actually not making a connection. Let me show you what I mean by that. So it looks like we have contact, right? But there's actually no contact whatsoever, because the actual connector of a transistor is located here. So by making it go to here, it's not actually making a connection. So this is no good. So let me get rid of stuff that is no good. And this time I will make it in the correct way. So I have to connect the wire to the connection point, and the same way over here. Now, if you see something that's red in color, it usually means it's not good, but that's okay because the circuit is not completed yet. So it's okay to have some red stuff in here. So now we look at the N-type transistors, okay, so which is this one, and we know we need 2 of these. So once again, we use Control D after the selection to make another one. And I am going to select just the transistors this time, and kind of move it out of here. And then this time I also need to rotate it, but I need to rotate it counterclockwise this time and not clockwise, because if you look at the diagram very, very carefully, you will see that the p-type transistors have the arrow pointing down, and then the n-type transistors have the arrow pointing up. So this time I need to change the facing, not to south but to north, like so. And unfortunately, that also automatically makes a connection between the 2 transistors. So let me move these off a little bit, and then we get rid of this connection, which we need eventually, but I do want to show you that sometimes when you rotate things and move things around, it will automatically make connections when you may or may not want those connections. So once again, I'm changing the gate location, okay, just a little bit, and turn it like this. And then we also need a ground. So you can look at ground as the negative terminal of a battery, okay? So we have the positive going here, the negative going here. Okay. All right. So another explanation of what this symbol is representing, this is called power, okay? I mean, really it's just called power. But you can look at this as the father or mother or parent of ones or true and stuff like that. It is the source of ones. And by comparison, the ground is the parent of all the false, okay? All the zeros and all the low voltage, okay? So now we just have to complete all the connections. Now remember, you have to go from the connection point where the your mouse pointer turns into a circle, okay? And kind of make sure that you make connections only to those connection points, like so. And now we see, these two dots over here. So those dots are actually significant because it is representing that this is an actual junction of the three wires, coming to the same place. Because we can have flyovers, which I'll explain in just a little bit. So now we'll get rid of these text here. Okay, so the first question, I'm pretty sure that question is in the mind of many of you, okay, that's only natural, is why do we change the phasing? Excuse me, why do we change the orientation of the arrow? So as it turns out, a P transistor, this is a really easy way to remember it. A P-type transistor controls the flow of something positive, and an N-type transistor controls the flow of something that is negative. So if you have taken a class in physics, you know that the positive end of a battery is quote unquote the source of positive charge. So positive charge goes from power in the direction of ground. Okay, so that's why with a P-type transistor, the source is where you get the positive charge, and the drain is where you want the positive charge to go once the gate says, yep, this is open, go. Okay. What about the N-type transistors? The N-type transistors, which are this one and this one over here, as the name implies, it controls the flow of negative stuff, okay? So in the case of a battery, it would be the flow of electrons, okay? So electrons flow in the opposite direction of charge. So electrons goes from ground to the positive end, because electrons, when you look at the symbol of electrons in chemistry, it is E and then with a superscript a minus, because electrons hold a negative charge. Okay, so this is why the source of N-type transistors, would point to the ground end, and the source of a P-type transistor points to the power end. Okay. So do we have any questions about this part? Because I know this part can be a little bit confusing. We got some question over here. Oh, okay. I think we just got one more person joining the server as we speak. So I'm gonna go to my server settings and let that person into the recording. Oh, actually we got two. So we got Andrew. And yep, I think that's him. Okay. All right. So we got yet another person joining the server as we speak right now. Okay. All right. So now we need to hook up this stuff here. So we have stuff connected to the source of everything positive. We have stuff connected to everything that's negative. But what about the other stuff? We got 3 pins that we need to connect. This is where we draw, or this is where we get input pins. Now you can get an input pin from here as well. Okay, so there's a difference between the two. If you get a pin from here, the configuration is a little bit different from getting a pin over here. I personally would recommend getting a pin from here, which is the tool bar on the top, instead of from the catalog of parts over here. This is an input pin, this is an output pin. So an input pin is a square and an output pin is a circle. So as the name implies, an input pin specifies input. So you can look at the input pins as passed by value parameters to a function. They supply information for a function to process. So in this case, these are the ones connecting to the gates. So one connects to this particular gate of this transistor and also connects to the other one over here. And then this one connects to the other two gates of the other two transistors. So this is where I'm going to cross over this wire over here. So observe very closely. So I cross over like so. But you don't see a bubble over here. You don't see a dot like you see over here and also over here. So when you see the crossing of wire but without a dot, that means we have wires that are basically flying over each other. They are not connected. Okay, so the horizontal wire and the vertical wires are not connected in this case because of the absence of a dot. Okay, so this is how you read this type of diagram. And we also wanted to connect to the other transistor, which is over here. And the output pin, okay, so this is our output pin. We want the output pin to connect to this junction. So it really doesn't matter, whether I connect it to here or even here, because they are considered to be the same. Oh, I take it back. You have to be from here and between here and here and here. Okay, so anywhere within those three places would be fine. So what we are going to do now is to look at this circuit diagram and go like, hey, it's working. Okay, I'm just looking at the time. We got 10 more minutes, which is perfect because I can explain what this circuit is doing in 10 minutes. All right. So the circuit is done. Okay, I didn't label the parts. So if you want to label the parts, it's pretty easy. You just click on the part itself, and then you okay, so it doesn't have a label here. So to do the labeling, you just use a text tool. Okay, so I think this is Q1, this is Q2, and so on. So you can just go ahead and use text to label the transistors. The pins, on the other hand, have their own labels. If you click on a particular pin, you can see one of their properties is a label. So we can say this is X, we can say this is Y, and this is our output. Okay, so we can use anything as the label. So we can just call it output. So we got our circuit here. So now the question is, what is the behavior of a transistor? How do we turn it on and how do we turn it off? Okay, the help inside LogicSim gives you an explanation. I'm just switching to the help that we saw earlier. Okay, so this gives you an explanation, but I'll give you my own explanation. So let me switch to my text terminal, and I cannot Control-C that one because otherwise I'll kill LogicSim. So, but I can do it like this, and this is CISP310. Okay. So I'll give you a universal description of how transistors turn on and how transistors turn off. Okay, and this applies to both P and N type. But the important part is you have to identify which one is the source, which one is the drain, and which one is the gate. Okay. For both N and P type transistors, okay, and I have to remember what it is. Okay, if the gate has a voltage that is different from the source, the transistor conducts. Now, when we say the transistor conducts, there are other ways to refer to the same thing. You can say that it closes the circuit. Okay. You can say, it is on. Okay. So that means if you want to turn off a transistor, what do? Just let me switch back to my Discord so I can see your answers. Where's my Discord? Uh-oh. Did Discord die? Nope, it's still here. There we go. Nope, that's not Discord. Uh-oh, Discord died. Okay, I am so sorry that Discord died on me. Let me go back and reshare the screen. So, screen share, going back to the OBS screen, go live. There we go. All right. Okay, I do apologize for the technical difficulty, but YouTube has been recording the entire time, so we got, at least we got that. Yeah, I don't know exactly what is going on, but Discord is not super reliable. You know, it just kind of craps out. I'm thinking every lecture, because it did the same thing, you know, earlier this morning too. Anyway, so we get back to this note here. So let me just kind of re-explain it. So when you look at both the N and P type transistors, if the gate, okay, the pin that is kind of sticking out, not part of the line, okay, not part of the straight line, if the gate has a voltage that is different from the source, then the transistor is quote unquote turned on, which means we are closing the circuit. We are letting stuff to flow through the transistor. Okay, so this description applies to both the N and also the P type transistors. Okay, so this allows us, okay, so I'm moving this off the screen, at least a portion of it off the screen right now, so we can actually look at the circuit. So when we get back to this circuit here, okay, and looking at the current state, we want to say, well, why do we see a 1 as the output? Okay, so we look at the transistors one by one. So I'm going to use the selection tool to look at each one, you know, individually. So I'm looking at this transistor, the one being selected right now. The source of this transistor is which one? If I look at the three connectors, the north, the south, and also the west, which one is my source? The north one, very good. So the north one is directly connected to power, which is basically a 1, okay? You know, it's the high voltage, okay? And the gate is connected directly to a 0. So they are different. Whenever the source and the gates are different, the transistor is on. So Q1 is turned on, which means this is actually conducting, okay? The same thing applies to Q2, because Q2 is actually in the same scenario, even though the gate of Q2 is connected to another input pin, but it's also 0. So when you compare the source of Q2 versus the gate of Q2, they are also different. So that's why Q2 is conducting as well. So now when you trace the wire coming to the output pin, then you can see how it has two completed paths to go to the power, which is basically a 1. And as a result, the output pin is now actually connected through the transistors Q1 and Q2 to a 1. And as a result, the output pin has a state of 1. Is that explanation okay, or does anyone need a little bit of a different explanation? It might take a little bit of time to sink in, and that's why everything is recorded. What would it show if the output was on the blue section? Oh, okay. Well, we can always find out. Okay, so Daniel is curious about what do we see, you know, if we were to connect an output pin to the blue section. And that is what you see. You see an X, which is basically saying we don't know what it is. Okay, we don't know whether it's 0 or 1, you know, because it is actually what we call floating. It is as if you have a wire. Okay, just think of you have a copper wire. Okay, you're not connecting the copper wire to a battery or anything, okay? And then you're using a voltmeter and use one terminal of the voltmeter to attach to the copper wire, and then the other end you can connect to something else, okay? Then I'm asking you, what are you measuring, okay? With that voltmeter, and well, the voltmeter, typically will show something that's close to 0, but most of the time, it will fluctuate just a little bit, because a conductor is actually an antenna, okay? It's picking up electromagnetic waves, just through the air. So if you are to turn on a microwave, or a cell phone, is ringing close to that copper wire, that electromagnetic field or the changing electromagnetic field would actually induce current on that copper wire, and then you'll start to see voltages and stuff like that. And that's basically what the blue section is. It is not connected to ground, it is not connected to power either, because this transistor, this one here, is turned off. Okay? Oh, you're welcome, Daniel. But this is a good question, okay? Because we are now looking into this particular transistor, which I'm going to call it Q3. I think that is consistent with the diagram in my notes. So now we want to look at Q3 and ask, what about Q3? What is it doing? Okay. So when we look at Q3, we want to look at two things, right? We want to look at the source, and we want to look at the gate. The source of Q3 is pointing to the south, which is this terminal here, and it has an unknown voltage. Okay, we don't know what it is. Okay. But it doesn't even matter, because there's another transistor in series with Q3, which is this transistor over here, which I'm going to call Q4. Okay. So when we look at Q4, we definitely know what Q4 is doing, or really is not doing in this case, because Q4 is an N transistor. With an N transistor, well, with any type of transistor, the from and when you look at the arrow, as from and to, the from is where the source is. So this is the source of Q4. This is the gate of Q4. See how they are of the same color? They're both dark green. That means they're the same voltage. If the source and the gate of a transistor, regardless of the type P or N, are the same, the transistor is off. Okay, so that means Q4 is quote unquote off. It is not connecting. It is opening the circuit. So that means there's no electrical connection from here across the transistor to ground. If one transistor in series of the two is off, then it doesn't matter, because we do not have a path to go from the output pin to ground anymore. So the output pin is only connected to power, but not to ground, and as a result, the output is a 1. Is that okay? Does that explain the current configuration of this circuit? All right, excellent. So I'm going to go over time just a little bit, because I want to show you how to turn the output to a 0. Okay? Okay, thank you. So if I want this output to be a 0, that means I need a connection through this wire, through Q3 as well as Q4 to ground. So that means I have to turn on Q4. Now to turn on Q4, its source is already connected, hardwired to ground. I cannot change that. But I can change the input pin, which is Y, that is connected to the gate of Q4. They just have to be different in order to turn on Q4. So I can turn on, Q4 by, now this is also important. This is called the poking tool, the poke tool. The poke tool is really useful because it allows you to change the state of input pins. So if I use the poke tool to click on an input pin, it will basically toggle the state of the input pin. So now Y as an input pin is a 1. So now the source of Q4 and the gate of Q4 are different. So Q4 is now connecting. But now you look at this diagram and go like, hey, but the output is still a 1. Why is that the case? Well, that's because Q3 and Q4 are in series. If you look at Q3, which is this guy over here, Q3 has the source being, now it is connected to ground, which is 0, but the gate which connects to input pin X is also a 0. So now you have the gate and the source being the same again for Q3. So Q3 itself is open, it is off. And because Q3 and Q4 are in series, if at least one of them is opening the circuit is open. So that's why, the output pin is also still not connected to ground, because one of the two N-type transistors is off. What about the P-type transistors? Well, of the two P-type transistors, one is on and one is off. The one that is on is Q1, the one that is off is Q2. But that's okay, it's not a problem, because Q2 and Q1 are connected in parallel. You just need at least one of them to be connecting in order for the circuit to be connected, in order for the output pin to connect to the power. So in this case, even though Q2 is off, because the state of the gate and the state of the source of Q2 are the same, so Q2 is off, but Q1 is on, so all I need is at least one path to get to the power. So the output pin is still measuring a 1 at this point. So in order for the output pin to connect to 0 or connect to ground, I need to do two things. I need to turn off Q1 and I need to turn on Q3. But guess what? I can do both at the same time, because the gate of both of those transistors, they both connect to input pin X. So when I flip X from a 0 to a 1, I turn off Q1 and at the same time I turn on Q3. So now we have Q3 and Q4 being on, they're both connecting. So now we are connecting the circuit from the output pin to ground, but we are also at the same time disconnecting the output pin from power, because both Q1 and Q2 are off at this point. There is no path to power at this point, so the output pin basically has no choice but to say, I'm measuring the same voltage as ground, because it has a path that is connecting it to ground. So that basically completes the analysis of this circuit. And one of the questions that you guys might have at this point is, how is this useful? Okay. Well, the answer to that question is not Google. It is not the help in LogicSim. It is, okay, I'm waiting a little bit for you guys to chime in. Andy is typing. I've got to wait. Is this example just to show how the two different type of transistors work? Partially, yes. Okay, but partially it is showing you how figure 3, which is this circuit, works, because if you read the rest of this module, it will go through the same analysis that I just went through verbally. This is the text representation of exactly the same discussion, and then I'll give you a truth table. Okay, so if you read through the text, we'll talk about this on Thursday, but I want to give you a preview of what this is. Okay, so we'll go through a truth table, and then eventually we'll say, oh, okay, so all of these transistors are doing the same thing as this operation in C and C++. Let me retype this in the text terminal so it's easier for you guys to see. Okay, so basically we are saying the output is the negation of input pin X logical and input pin Y. Okay, that's what the circuit is doing. Okay, there are two significance to this particular claim. One is, hey, Tech, you're not looking at a circuit diagram anymore. You're using logical operators that we already know in C and C++. That is important because now we are connecting physical devices to abstract operations in a programming language. Okay, so this is big. Okay, it is important. This operation is also called NAND, N-A-N-D, which stands for, okay, let me wait for it, which stands for not and, okay, or negated and. Okay, that's what NAND, N-A-N-D, is representing. Then you go like, NAND, I mean, that's a really obscure operator. We have never learned about the NAND operator. Is it really useful? So we're going to talk about this on Thursday. Okay, so the NAND operator turns out to be actually a universal operator. We can use NAND operators to replace simple negation, simple conjunction and also simple disjunction or. All we need is NAND. Really, we just need NAND. We don't need no stinking negation. We don't need no stinking conjunction nor disjunction. We just need NAND. So that is kind of cool, but we'll talk about that on Thursday. But don't leave just yet, okay? We got one last thing to do, which is for me to open up the lab of today. So this is the lab for today. You cannot see it yet because it is not open yet. So I'm gonna set it up, okay? So this is the lab where it will give you instructions of where to download CISP310.jar and how to make use of it. And for the most part, I have just demonstrated how to use LogiSim. So this really should not be a very complicated homework assignment. You have until Thursday 7 p.m. to complete this assignment or this lab. But I will be online for the next, I'll be online until 9:50 p.m. So if you do it right away and you have questions, I can answer right away. So that's the synchronous portion of the lab. The lab has its own passcode, which is LogiSim. Okay, so kind of remember that. And now I will give it a due date, which is August 27th. So you have 2 days to complete this one. 7 p.m., which is the start of our synchronous lecture. So this is pretty much how the labs are all going to be set up. Each one is going to be, the due date of the lab is going to be right before the synchronous lecture starts on the next synchronous lecture. Some of these will take longer and I'll give you a little bit more time to do it, but this one really should not be taking that much time. And the passcode, once again, the passcode to the lab is LogiSim itself or lowercase. Okay, so you have to kind of write it down because when you try to get started with this one, it will ask you about that. And now when I click Save and Publish, you should be able to refresh your Canvas page and be able to see LogiSim set up as your lab activity for 2 days, basically. So you got 48 hours. No, I take it back. 48 minus 1 hour and a half to do it. And I will stay online. The lecture portion is done, so I'm going to turn off the live stream in just a little bit. But I will stay online until 9:50 p.m. today. So if you want to get started on the lab right now, which I highly recommend, go ahead and do it, and then I can answer questions on Discord. I got one direct message. Oh, okay, I'm still peeking a little bit on Discord. That's because OBS and Discord are not connecting from the same source. So let me just make that adjustment. This adjustment is going to be persistent until I change it. So this way I can stay with this next time so I don't peek out as much. Okay, there we go. All right, so the lecture is done. Let me go back to the Discord text channel. There are no questions right now. So I'm going to disconnect from the voice channel, and then the screen share is going to terminate as well. And I'll go ahead and also stop the YouTube stream at the same time. But I want you guys to get started on the lab, now if you can. And so I can answer questions right away. And that's kind of why the synchronous session is good, is because I can basically answer questions right away. All right, I got 2 more text messages coming in, so I want to make sure that those are not applicable to the whole class. So one is, oh, okay, this one is good. Okay, so don't go just yet. I do not know who I can drop until tomorrow at 7 p.m. So by tomorrow at 7 p.m., I will use the roll-taking mechanism to see who missed the first class. And those people will be dropped. And then I will start to move people from the wait list into the class. So that's when you will know whether you can add to the class. And I'm going to use the same order as on the wait list. So I'll just be moving people on the wait list as ordered on the wait list into the class. But I won't know until tomorrow at 7 p.m. Okay, so that's one question, and there's one more. So the other question is, what do I suggest you guys read before Thursday? So if you go to the Canvas site, we are close to ending Physical States, Truth, Numbers, and Computers. So what I want you guys to read is over here, okay? Values, numbers, and bases. That module is about base conversion. Well, it's actually more about how we represent values using numbers. Now, isn't that phrase a little bit confusing? You know, aren't values the same thing as numbers? Well, no, it's actually not the case. A value is an abstract thing, okay? And a number is a representation of that abstract thing so that we can communicate with other people or the computer and stuff like that. So, so that's where we are heading on Thursday. So I think on Thursday we'll be able to get into base conversion, you know, numbers and stuff like that. So if you have time, which I hope that is the case, try to read up to that module. So I think that answers another question. And there are, okay, I'm just looking at the Discord text channel here, and there are no more questions. All right, excellent. So I'm gonna stop live stream on Discord and also end the stream to YouTube. So if you guys want to review today's lecture, it is on YouTube right away, I think. But the closed captioning won't be there until, I'm guessing it will take maybe 12 hours, 24 hours for the closed captioning to appear. Tom is typing something. Let me just kind of make sure that it's not applicable to the whole class before I disconnect from the voice channel. Okay, so Tom is saying, as for people on the wait list, is there an estimate of how many will be added in? Well, that depends on how horrible I'm teaching this class. Because if I'm doing a really bad job teaching this class and everybody's saying, I have no idea what TAC is saying, then I'm thinking most people on the wait list can add to the class. But I don't know, how many people are going to drop from the class and how many people are not going to be absent on the first day. So I really cannot give you an estimate just yet. So I'm sorry, Tom, I cannot answer really that particular question because I can't really anticipate how many people are going to drop or miss the first class. Okay, you're welcome. I would try my best to answer the question, but this is one of those questions where it's really, I don't have an answer. All right, cool. So I'm going to stop the share screen and also the voice channel both at the same time, but I'll stay on the text channel. So if you guys have any questions, I will correspond to you. I will basically answer your question using the text channel on Discord.